Welcome. In this video, I'm going to walk you through the matrix computations for an ordinary least squares regression equation for the unstandardized regression coefficients and their standard errors. So looking at the formula here, it's fairly compact. We have an X matrix, which represents a matrix of the predictor variables. So we're working from the raw scores here. So we have three predictor variables in this equation. So the X matrix is basically a matrix that contains a column for each predictor variable and also a column for the intercept. And we also see in this equation that we have a Y matrix, which is basically a column vector of the outcome dependent variable, criterion scores, whatever you want to call it, for the Y variable. So those are the two matrices that we will deal with in this equation. So the first step is we want to take the transpose of the X matrix. So to do that, we just kind of flip it on its side. We can use a computer program or Excel to do the heavy lifting for most of these matrix manipulations. And here I've told Excel to kind of flip that matrix on its side, so then we can multiply the transpose by the X matrix transpose by the X matrix. So I've done that. And once we do that, we should get a 4 by 4 matrix, which we need to invert. So inverting the matrix can get really tedious, but fortunately, if you have access to even Excel, you can tell Excel to invert the matrix for you. And then we have here the matrix inverted. The next step is to multiply the inverted X transpose times X matrix by X transpose once again. And we'll get a rather large matrix for that. And then finally, the last step is you multiply the product of the X transpose, the inverted X transpose by X matrix, which was multiplied by the X transpose matrix, and then finally multiplied by the Y column vector, and that will give you your unstandardized regression coefficients. So the first coefficient I have here represents the y-intercept. There we have the coefficient for the first predictor, the coefficient for the second predictor, and the coefficient for the third predictor. So we can use those coefficients to compute the predicted scores, which is what I did in this column here. So I have the predicted scores by simply taking the intercept and adding to the intercept the product of each score and the coefficient for each variable. So 2 times the coefficient for the first predictor, 6 times the coefficient for the second predictor, and then 6 times the coefficient for the third predictor. If we add those together, we'll get a y-predicted score of 75. So you can do that rather quickly in Excel for each case. And then you can also get the error, which is going to be the observed score subtract the predicted score. So we'll need that to compute the standard errors. I'm assuming you want the standard errors of the regression coefficients as well. So the formula for that involves taking so we have the column vector for for the error, we'll take the transposed column vector for the error, multiply it by the column vector for the error, divide by the degrees of freedom, which is number of observations, subtract the number of predictors, and then subtract 1, and multiply that by the transposed matrix of the difference scores times the matrix of the difference scores, and then finally invert that matrix and multiply it by this, which is basically the variance of the error. So the first thing, I'm going to start with this part of the equation. And so I computed the difference scores. The difference scores are basically just each observation subtracting its mean. So I took the raw score for x1, subtracted the mean for x1, and I got negative 2.2 for the first observation, negative 1.2 for the second observation, so on and so forth. The same for the second predictor. I took 6 minus the mean for the second predictor and got 0.9 for the second case. Second predictor got 1.9, and so on and so forth. So these are just deviations from the mean. So I did that for the 3 predictors. I also did it for the outcome variable, although it's not needed for this equation. All right, so then I did this part of the formula first. We have the transpose difference scores here. So basically took the matrix of these difference scores, and we don't need a column for the intercept here because it will be 0 because we're dealing with difference scores. And so I flipped that on its side, take the transpose, and then multiplied it by the difference score matrix, and I got the resultant matrix, and then finally I took the inverse of that matrix. Now I have the inverse of the matrix, and I need to now multiply that by the transposed error matrix times the error matrix divided by the degrees of freedom for the test. So I have the error from earlier, which was the difference between the observed and predicted scores. So I have that matrix, so I need to transpose it and then multiply it by the untransposed form. So I take the transposed version of the error scores and I multiply it by the column vector of the error scores, and I get the resultant product, which I then need to divide by the degrees of freedom. So here that's n minus k minus 1, which our number of observations were 20, our number of predictors was 3, and then minus 1, so I'm taking 20 minus 4. So I'm taking the product of the transposed error and the error vector itself and dividing that by n minus k minus 1, and I basically get then the variance of the prediction, error in prediction, which I can plug finally into the equation. So here I have plugged that part into the equation, and now I multiply it by the previous matrix, which was the inverted product of the transpose difference scores times the difference scores. And this matrix in the diagonal is how I can get the standard errors of the regression coefficient by taking the square root of the values in the diagonal. So the first value in the diagonal, the square root of that is 3.01. Next is 2.88 roughly, and next is 2.39 roughly. And those are the standard errors, which I can then divide into the regression coefficients to get the resultant t observed values for the regression coefficients, and I can use those to determine the p-values for those regression coefficients. So that was kind of a long and not so fun journey to compute the regression coefficients and their standard errors using matrix equations. Fortunately, in this day and age, there's no strong need to have to do this, but occasionally we might become, for whatever reason, curious as to how the coefficients come about using the matrix computations. So I hope that you enjoyed that video as much as I enjoyed it, and have an excellent day.